Good evening, everyone. Welcome to the third live session for the course Concrete Technology offered by NPTEL. So, I am Harshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay, and I will be taking weekly live sessions for this course for the entire course duration. So, in today's session, we'll first revisit the last live session that was for the week two content. Just to quick recap, then we look into the things that were covered in the week three content of the course. So we will the week three content that we will discuss today is divided into three segments. First is basic overview of aggregates. Second is aggregate characteristics, which includes packing density, fineness modulus, and surface modulus. And third will be the properties of aggregates. In between, I will have some questions related to the content. So in total, there will be around 13 to 14 questions today. Some are theoretical and some are numerical questions. And finally, we will conclude the discussion and I will try to address any other queries post discussion. In between, if anyone has any doubt, you can unmute and speak or you can type in the chat box. And I hope it things will be clear throughout the session. So last week we concluded the second week of the course where we started with the discussion of different types of water and porosity in the cement paste system. For water, we talked about three types of water: capillary water, gel water, and chemically bound water. And we saw the representation of these water in a Feldman Faraday model of CSS structure. Similarly, we characterized porosity in three size ranges: capillary pores, gel pores, and macro pores, and we saw them on dimensional scale representing solid and pore volume in hydrated paste system. Then we talked about properties of cement. We listed chemical and physical properties. So physical properties are nothing but the end result of chemical properties, and they are important in determining the suitability of a cement for a specific application, and they are also important for ensuring that desired quality of cement meets the standard guidelines that have been formulated. So we talked about different physical properties of cement. Those were normal consistency, specific gravity, soundness, fineness, setting time, and compressive strength. And we saw how IS code defines these properties in terms of how testing is conducted and what are limits that has been set for OPC cement regarding these properties. Then we talked about different types of cement based on the composition of cement. Cement class can be classified into different types, and these classifications, why they are important, because they help us to choose the best cement suited for a particular application need. So in this type of cement, we discuss three classification: ASTM based classification, special purpose cements, and blended cement. In ASTM, we talked about type 1, which is conventional OPC, type 2, which is a modified Portland cement, type 3, which is rapid hardening Portland cement, type 4, which is a low heat Portland cement, and type 5, which is a sulfate resisting cement. So, based on the composition of cement, we saw how the application domain changes for these ASTM classification. In special purpose cement, we talked about super sulfated cement, high alumina cement, white cement, and expansive cement. And finally, in blended cement, we first understood how blended cement came by looking into the history of hydraulic lime and volcanic ash. And then we just introduced ourselves to fly ash, GGBFS, and silica fume, how they are obtained and why they show cementitious property. Okay, so this was about everything that we discussed last week. Now we'll see the next part of the equation of concrete that we wrote in the week one of this in this session. And so after discussing about cement and water, we will talk about aggregates in concrete. So how we define aggregates? So simply saying aggregates are nothing but these are solid particles other than the cement paste which does not contribute or participate in the hydration reactions, and these solid particles, they are known as aggregates. Okay, they are inert, they are not participating in the hydration reaction, but they are present in concrete. Okay, now even though they are not contributing in hydration reaction, then why aggregates are needed? Okay, so in simple terms, if we say, they provide the dimensional stability to concrete. Okay, why this is important? Because we know cement hydration is an exothermic reaction. Okay, and this can lead to shrinkage and cracking issues in concrete because of heat release from concrete. Okay, and what aggregate does, it helps to reduce shrinkage and prevent cracking in concrete as concrete cures. How? So now this issue of shrinkage, you may not see in small samples like in 50 cross 50 cube that we prepare in laboratory, or a small like 100 side cylinder that we prepare. But when we talk about bulk concrete, like large concrete blocks, shrinkage becomes a very big issue if if we just use cement for making concrete and no aggregates. Okay, because this hydration of cement is exothermic reaction. So inside the concrete there will be high temperature and outside there is low temperature, and this developed thermal gradient, it will give rise to shrinkage stresses which can crack the concrete. So what aggregate does, it helps to reduce this shrinkage and prevent cracking in concrete by reducing the amount of cement that we add for making concrete. Okay, so they reduce the apart from reducing the shrinkage issue, they also reduce the overall cost of concrete by acting as a filler, and they minimize the amount of expensive cement that we used for concreting. Okay, so generally 60 to 80% of volume of concrete, it is occupied by aggregate. Okay, and thus they are very important part of concrete. Now, there are various sources from which we can obtain aggregates, or we can say the geological aspect of aggregates in general is like from aggregates can originate from different natural rock formation, and they can be igneous rocks, sedimentary rocks, or metamorphic rock. From each of these rock classification we can obtain aggregates. The ones which you get from igneous rock, they can be granite or basalt aggregates. The sedimentary rocks includes limestone and sandstone, and metamorphic rock includes marble and quartzite. So quartzite, if you remember when we talked about cement testing, compression testing of cement, we talked about quartz sand, which we used in three grade 1, 2, and 3. So this is one of the type of aggregates that we are using. Okay, so apart from the source of rock, other broad classification of aggregate includes natural aggregate, manufactured aggregates, and recycled aggregates. So these are also different sources from where we are getting aggregate. Natural means those which are obtained from natural sources like river beds. In flowing river, the depositions that happened on the river bed, that sand we use as fine aggregates. Then there are quarries and glacial deposits which are also used as crushed stone and limestone aggregates. Okay, manufactured aggregates are those which is like from natural sources we collect the aggregates and we crush them or we process them in industry to get a desired size or desired shape. So those aggregates will come under the category of manufactured aggregates, like crushed granites, expanded clay, artificial sand. All these are manufactured aggregates. And the third and the very important category, which is now gaining significant attention, is the recycled aggregates. So once we construct a building, when we demolish this building, the waste that is generated from the building, from those waste, like we have used concrete for making this building, so once we demolish, we can recover the aggregates that we have used in the building, and the aggregates that we recover after demolishing a concrete structure, those aggregates are known as recycled aggregates. Okay, so we make them by crushing the concrete bricks and demolished structure. Okay, so these are recycled aggregates. Now, there are certain properties of aggregate which are independent from the parent rock, okay, from which it is obtained, but they still play a major role in concrete performance and durability. And these properties are size, shape, and surface texture of aggregate. Okay, so according to Indian standard IS 383, we classify aggregate into two subcategories based on size. Okay, there is coarse aggregate and there is fine aggregate. Okay, So the aggregates which have size greater than 4.75 mm and up to 50 mm, these are known as coarse aggregate. And the aggregates which have size lower than 4.75 mm and greater than 75 micron, these are known as fine aggregates. Okay, so in coarse aggregate again we can have manufactured, natural, and recycled aggregates, and in fine also we have river sand or manufactured sand which are available. Okay, and based on the density or the properties of these aggregates that we are getting, it we can classify these aggregate into lightweight aggregate, normal weight aggregate, or heavy weight aggregate. And these properties of aggregate, they again define where we want to use the aggregate. So just like we talked about cement, the properties of cement are useful, the composition of cement is useful for us to understand the hydration of cement. Similarly, the size, the shape, and the surface texture of aggregates are also useful for us to understand the application of aggregates in concrete, like in which project or for which property need which aggregates are suitable for us. So now in this classification based on size, we saw there is coarse aggregate and fine aggregates which are distinguished based on the representation of size. Okay, so how we measure the size? Okay, we told coarse aggregate is coarser than 4.75 mm and fine aggregate is of size lower than 4.75 mm. So how we are measuring the size of a single aggregate? Okay, so these size we measure in terms of square sieve size. Okay, so these sieves are these circular uh, uh, mesh kind of plates, okay, which is used like a wire mesh, which have square openings of certain size. Okay, so there are different sieves which have different square openings of different sizes, and based on the passing ability of aggregate through this sieve, it helps us to define the size of aggregate. Okay, so we can see here the set of sieve. Okay, the topmost sieve has the biggest opening. Then as we go down from top to bottom, the size opening in these square sieves, they are decreasing. Okay, so the topmost sieve has the largest opening while the bottommost sieve has the smallest opening, and at the base we have pan. Okay, so aggregates, when we classify aggregates based on size, we pour aggregates at the top. Okay, and these sieve, they arrange aggregate in their descending order of their size. Okay, so suppose we pour 1 kg of aggregate, some will retain on this sieve, some will retain on this, some will retain on this, similarly till the end. Okay, so we will have a size gradation of aggregates, and this gradation of aggregates using sieve, this is known as sieve analysis. Okay, so in sieve analysis, what we do, we weigh the retained weight of aggregates on each sieve, and we calculate percentage retained and cumulative percentage passing factors. Okay, so how much percentage is retained on this, how much percent is passing through this, so these kind of calculations we do. And then based on Indian standard or American standard guidelines, we define these aggregates. Okay, so although suppose this is my sieve having a square opening of 4.75 mm. Okay, so all those aggregates which are passing through these sieve, they will come under the category of fine aggregates, and all those aggregates which are retained above this sieve, it will come in the category of coarse aggregate. So you can see in fine aggregate we have 4.75 mm passing, 2.36 mm passing, 1.18 passing, 600 micron passing, 300 micron passing, and 150 micron passing. While in coarse we have 80 mm, 40 mm, 20 mm, 10 mm, and 4.75 mm. So this is like a margin for us. Above this is coarse, below this is fine. And now, once for sieve analysis, once we get the information of how much aggregates are passing and how much aggregates are retaining, we plot a grading curve. Okay, which is cumulative percent passing versus sieve size. Okay, so on the x-axis we have different size of sieve, and on y-axis for each particular size, what was the cumulative passing. Okay, so for this sieve, the cumulative passing will be all the aggregates which are there in the bottom sieve. Similarly, for this sieve, the third sieve, all the aggregates which are there in these set of sieves will be its cumulative percentage passing. So all those calculation we do, and then we make a plot. Okay, and this plot is known as grading curve for aggregates to analyze the particle size distribution of aggregate. Okay, so based on the type of grading that we obtain, there can be three aggregate types: well graded, poorly graded, and gap graded. Okay, so in well graded, there is mixture of big aggregates, small aggregates, smaller aggregate, and smallest aggregates. So all has a good mixture of different sizes of aggregates. So if there is good mixture of different sizes of aggregate, then we say it is well graded. In poorly graded, they are mostly aggregates of same size. So all are like big aggregates, all will be like very small aggregates. There is no distribution in size. So those are poorly graded aggregate. And gap graded means there are very big aggregates and very small aggregates. There is no intermediate size. So those aggregates are known as gap graded aggregates. Okay. So among these three categories, the best one for us is the well graded aggregates because they will have proper compaction, strength, and workability. So we'll be talking more about this and in the session ahead. So just remember these terminologies for now. Okay, when we'll talk about aggregate classification, multi-sized aggregate, how they affect the packing and everything, at that time the difference between these two or these three, all these three will be clear to you. Okay, so now just as an exercise, try to guess which grading curve represents which type of aggregate. And in the meantime, if anyone has any doubt regarding that discussion till now based on source of aggregate and aggregate gradation, you can ask. I see there is some. Any doubt in the discussion till now? I hope everyone are clear about the source of aggregate based on rock and the based on natural or manufactured or recycled, and how aggregates are classified based on size. Sieve analysis, how we do sieve analysis, what are sieves, and what is grading curve. Okay, if it is clear, just tell me which this first curve, it will represent which graded aggregate. Is it well graded, gap graded, or uniform graded? We can insert here one more curve. Okay, suppose this is one more curve. Sorry, this is one more curve I have added. Okay, so this is fourth one. Okay, guess all four. One, two, three, four. What each curve is representing? Which kind of grading? Okay, first one is well graded. Let's see. Okay, first one is gap graded. Why? You can see there is high proportion of aggregates of around 0.1 mm. Then there is a flat plateau. It means that percentage of aggregate is weak here. And then there is high percentage of aggregate in this region. Okay, so there is smaller size aggregate, there is bigger size aggregate, but in intermediate sizes, there is no aggregate or very small portion of aggregate. Okay, so just see from the slope. Higher is the slope, it means that there are more aggregates in that region, okay, of that size. So this is why it is gap graded. There you can see a one steep slope, then there is flat, then there is steep slope, and then it is becoming flat. I have received few answers. Okay, what will be the fourth one? I have added four also. Okay, one is poorly graded. Okay, second one, let's see. So second one is uniformly graded. You can see there is continuous increase in percentage passing of aggregate from zero point 0.1 to 1%. Okay, so this is a uniform gradation. Okay, of all the aggregates, suppose that this batch has aggregate in this range only from 0.1 to 1%. Suppose we are talking about fine aggregates. Okay, so in fine aggregates, you can see there is regular increase in size that is happening with increase in sieve between zero point 0.1 to 1 mm. So that's why it is uniformly graded. Then third one, it is well graded. So you can see from the slope. Okay, slope is continuously increasing as size is increasing from 0.001 mm till 100 mm. Okay, so you can see there is regular increase in size. It means that all sizes of aggregates are present there. Okay, so that's why it is well graded. Okay, and the fourth one, it will be poorly graded. Why? Because you can see there is very small portion of aggregate up till here. Okay, and then there is a shoot. So this means that aggregate are like this. Very big coarse aggregates are there. Maximum portion of the aggregates are these very big coarser aggregates, while finer aggregates are very low in quantity. So that's why it is poorly graded. Okay, so you need to be careful in between 2 and 4. Okay, in 2 also you see a steep increase, but it is between two very close size fractions. Okay, while here you can see in 4 it is increasing slowly till from 0.001 mm till 10 or 12.5 mm, and then there is a steep rise. That means there are very big coarser aggregates. Maximum proportion is of coarser aggregates and very small proportion is of fine aggregates in it. Okay, I hope this question was clear how we understand aggregate grading. Okay, now just help me do the calculation. Okay, how we will calculate the cumulative percentage passing, and we will determine whether how much percentage of my aggregate are coarse aggregate and fine aggregate. Okay, so I have a sieve analysis data. I conducted a sieve analysis on 5 kg aggregate and I recorded this weights. Okay, so aggregate passing retained on different sieves. Okay, this is my sieve. Okay, suppose these are the sieves. Okay, and on these sieves we poured aggregate from the top. We let it vibrate for some time, and then we calculated weight on each sieve, how much aggregate has been retained on each sieve, and we recorded the weight. So on 40 mm 0 gram of aggregate retained, on 20 mm there was 750 grams. Similarly up till 0.15 mm there was 50 gram, and on pan at the bottom there was 50 grams. So this 50 gram is basically dust, we can say, very fine powder. Okay, so if you know the size versus retained weight, if you are doing sieve analysis, you do sieve analysis, you take weights and you get this data, how you will calculate the grading curve, how you will plot the grading curve from this. So calculate the percentage retain on each sieve, find the cumulative percentage passing through each sieve, and then determine what percentage of total sample is coarse aggregate and what percentage is fine aggregates. So just give it a try. I will like mute myself for 2 minutes and I will let you just give this question a try. Okay, at least 3 4 rows you try to make, if not complete. And in the meantime, if anyone has any doubt regarding this discussion that we have till now, you can just ask. Okay, so let's see how we do the calculation. So for this calculation for this question, we will first make a table. Okay, so this kind of table we can make. This is the data that is known to us. Okay, one more thing that is known to us, it is total aggregate weight is equal to 500,000 gram. Okay, 5 kg aggregate we took initially. Okay, so what we'll do, we want to calculate percentage retained, cumulative percentage retained, and cumulative percentage passing. So this column, with respect to this column, will give me my gradation curve and cumulative percentage retained. So up till 4.75 mm, whatever I am getting the value here, whatever value I will get here, it will define my course aggregate, and all the whatever value I will get from here to here, it will define my fine aggregate. Okay, so how we will calculate cumulative percentage retained? We know the how we'll calculate percentage retained. We know the retained weight on each sieve, and we know the total weight of aggregate that was poured. So percentage retained will be nothing but weight retained on the sieve into 100 divided by total weight 5,000. So for first sieve, for 440 mm sieve, it is equal to 0. Okay. Similarly, 750 upon 5,000 divide into 750 divided by 5,000 into 100, it will be 15%. 1650 divided by 5,000, it will be 33%. 1100 divided by 5,000 is 22%. 700 divided by 5,000 is 14%. 400 divided by 5,000 is 8%. 200 divided by 5,000 4%. 100 divided by 5,000 2%. 50 upon 5,000 is 1%. 50 upon 5,000 is 1%. So cumulative percentage retained, here it is 0. Here it is 0 plus 15. So that is equal to 50. Here it is 0 plus 15 plus 33. So it is 15 plus 33, which is equal to 48. Again, here it will be 48 plus 22. So it will be 48 plus 22, which will be equal to 70. Then 70 plus 14, which will be equal to 84. 84 plus 8 equals 92. 92 plus 4 equals 96. 96 plus 2 equals 98. 98 plus 1 equals 99, and finally we have 100. Okay, so above pan all aggregates will retain. Okay, that is known, that is how we can cross check our calculation. Okay, so you can say percentage retained over 4.75 mmc is our coarse aggregate. So 70% of the aggregates that we poured was coarse aggregate, and the remaining 30% is fine aggregate. Okay, now once you have percentage, cumulative percentage retained, what will be percentage passing? Nothing but 100 minus percentage retained. Okay, cumulative percentage retained. So 100 minus 0 is 100. 100 minus 15 will be 85. 100 minus 48, 52. Then 30, 16, 8, 4, 2, 1, 0. Okay, so when we'll plot this versus this, we'll get the sieve analysis or the gradation curve of our aggregate. Okay, I hope everyone are clear with this question, how we did the calculation. I'm really sorry, there was some network issues, I guess. So my screen got disconnected. Can anyone tell me at which point it was disconnected so that I can repeat.
Disconnected after you complete retained percentage for the pan.
Okay, so from after this column, second column.
Yeah, yes.
Okay, so I will repeat this part. Okay, so I hope everyone are clear how we calculated the percentage retained. The retained weight divided by total aggregate weight. Okay, now what will be cumulative percentage retained? For first sieve it is 0. For 20 mm sieve it will be 0 plus 15, which will be 15. So cumulative means all aggregate retained above 20 mm sieve. Okay, so it is 15 plus 0. Similarly, for 10 mmc cumulative retained, it will be 33 plus 15, which is 48. Then 48 plus 22, which is 70. 70 plus 14, which is 84. Then 84 plus 8 will be 92. 92 plus 4 will be 96. 96 plus 2 will be 98. 98 plus 1 will be 99. 99 plus 1 will be 100. So we can cross check our calculation also like this. Okay, it is 100%. So above pan we have 100% aggregate. Okay, so this is my cumulative percentage retained. So how, what is the fraction of coarse aggregate? Aggregates that are retained above 4.75 mmc. Okay, so that is 70% aggregate. So 70% of the total aggregate that we poured was under the category of coarse aggregate, and remaining 30% is fine aggregate. Okay, now what is cumulative percentage passing? So it is nothing but 100 minus cumulative percentage retained. So 100 minus 0 is 100. 100 minus 15 is 85. Then we have 52, 30, 16, 8, 4, 2, 1, 0. So when we will plot this cumulative percentage passing versus sieve size, we'll get the gradation curve like these. Okay, and from cumulative percentage retained, we get the knowledge of how much aggregate is coarse aggregate and how much is the fine aggregate. Okay, I hope this question is clear to everyone. Any doubt in this question? What is your doubt in retain part? Can you tell me? Okay, so what is percentage retained? Percentage retained means how much weight of aggregate was retained on a particular sieve divided by total weight of aggregate. So how we got 15%? It is nothing but 750 divided by 5000 times 100 to convert into percent. So that will give me 15%. Okay, so this means that 15% of total aggregate weight was retained on 20 mm sieve. Similarly, 33% of total aggregate weight, that is 1650, was retained on 10 mm sieve. So like that we did this calculation. Okay, so this is very important. Okay, whenever we get aggregates in laboratory from any source, this is a very important test for us. Okay, to calculate the gradation of aggregate, to know whether aggregates is uniformly graded, gap graded, poorly graded. Okay, and we need aggregates which are well graded or uniformly graded. Okay, well, gap graded and poorly graded aggregate are not desired. Why? We'll see later on when we'll talk about packing density. Okay. So based on the gradation profile that we obtain, that is cumulative percentage passing versus sieve size. Okay. Indian standard IS 383 in its table 2 has provided grading requirements for course aggregate. Okay, so it specifies the standard size of aggregate and corresponding percentage passing through different sieve sizes. Okay, so when we obtain aggregate gradation, then we say like what is in which grade it belongs, whether it is 63 passing aggregate or 40 passing aggregate or 20 So for that, is code has given this table. Okay, so once we get the percentage passing, cumulative percentage passing of aggregate, we check with is code and we check what values we are getting and what values code has reported. Okay, so for uniformly well graded aggregates, what should be the percentage passing for each category of aggregates is code has reported in this table. Okay, so we get our value and we compare here. So suppose this example that we took here, 100% was for 40, 85% for 25, 50 to 30, like that. Okay, so we can see at 40 sieve it was 100% for us. Okay, so it is in this two categories. Then at 20 sieve it was 85%. Okay, so it is coming here. Okay, so it is 20 nominal aggregate size is our category of aggregate. Okay, at 10 it is 0 to 20 for 20 nominal aggregate size. So at 10 12 data we don't have in our case. Okay, no, at 10 it is 52, so it is not in this range also. Okay, so right now the aggregate composition that we took, it is not satisfying what is code is saying. Okay, so there are single sized aggregate for that also, for mixed size aggregate for that also there is curve given. So this table we'll revisit once when we'll talk about packing density. Again we'll revisit this table so that it is will be clear to you what is single size, what is multiple size. That thing will be clear. Okay, so here my point was just that to let you know that gradation is important and Indian standard also takes gradation very seriously. Okay, so this tables these this table 2 was for course aggregate to define the grade of aggregate in terms of its based on its size. And then there is for fine aggregate also. So in fine aggregate we have different zones: zone 1, zone 2, zone 3, and zone 4. So based on the percentage passing of aggregate from different sieve sizes, we classify fine aggregate of for different zone. Okay, so zone 4 is the finest and zone 1 is the coarsest among fine aggregate. Okay, so we get that idea which kind of aggregate we are using in fine also, whether it is fine, very fine, or very coarse. Okay, so that idea we can get. And when there is all aggregates like coarse and fine together, that was our case. So we have all in one aggregate grading also, which is there in is code. Okay, so this is how code takes gradation of aggregate seriously. Now next, now to understand the grading of aggregates, there are two terms which are very frequently used. One is fineness modulus and second one is surface modulus. Okay, so first we'll talk about fineness modulus. So fineness modulus is nothing but a index number which is weighted average sieve number that gives us the rough estimate of average particle size for a given aggregate sample. Okay, and it is commonly used to categorize fine aggregates as coarse, medium, or fine. Okay, so it is just a number that we are getting. Okay, weighted average sieve number. So we know aggregate percentage retained on different sieves, and we divide it by number of sieves that we have. Okay, suppose we had taken 4 sieves, so percentage retained on all the 4 sieves divided by total of the number of sieves 4. So this gives me the fineness modulus of the aggregate. Okay, so and it is commonly used for fine aggregates to define whether they are coarse, medium, or fine. Okay, so how we determine, as it is written here, by adding the cumulative percentage retained on a standard sieve divided with the sum by 100. Okay, it is not 4, it is 100. My mistake. Okay, so we add cumulative percentage retained on each sieve and we divide it by 100. That gives us the fineness modulus. And how we interpret this number? By the quantity that we are getting. If my fineness modulus is less than 2.2, we say that it is very fine sand and which is not suitable for concrete. If it is between 2.2 to 2.9, we say medium sand, which is good for concrete. 2.9 to 3.2 is coarse sand, which is used for special application. And again, if it is above 3.2, it is very coarse sand, which is not suitable for concrete. So we need fineness modulus of our sand to lie in the range of 2.2 to 3.2 if it is suitable for concrete. Okay. Why very high and very low fineness modulus are not suitable? If we have very high fineness modulus, it will reduce the water demand. Okay, so what will happen, there will be chances that our mix won't be like compatible, or it won't match the required consistency that we need. And if our fineness modulus is very low, then it will increase the paste demand. Okay. Okay, so amount of cement paste that is required to keep concrete workable, it will increase that. Okay, so that is the problem of very high fineness modulus and very low fineness modulus. What we need is in this range. Okay, that is desired towards. And then there is surface modulus. So surface modulus is a parameter which determines the specific surface area of aggregate. So suppose this is my aggregate, then what is the surface area of my aggregate? It is known as, it is defined by surface modulus. Okay, the total surface area available per unit weight of aggregate. Okay, so surface modulus is nothing but total surface area of aggregates upon total volume of aggregate. Okay, and why it is important? It is primarily used to estimate the water demand and workability of concrete. Okay, so we know aggregates is not contributing in hydration reaction. Okay, however, if my aggregate is dry, it will absorb some water from concrete. Okay, so if we know the surface modulus of aggregate, we will know how much water demand is there for aggregate. Okay, and how it will affect the workability of concrete. Okay, so if there are finer particles, there is higher surface area, the same concept that we used for cement. If there is more surface area, there will be more water demand. Okay, if there are coarser particles, there is lower surface area. If there is less surface area, there will be less water demand. Okay, so this more water demand and less water demand, it is something that we need to take as a precautionary measure in mixture design. Okay, so we'll talk this later also, but I'm just touching up here. Suppose we take a W by C ratio of 0.4, okay, for preparing concrete, and we didn't consider the water demand of aggregate. Okay, so what will happen from this 0.4 ratio? Suppose it was 150, it was coming out as 160 kg per meter cube. So from 160, some water will be absorbed by aggregate. So my effective W by C ratio that was available for cement hydration, it won't be zero point 0.4, it may be 0.38 or 0.37. Okay, and if this changes, it can critically affect the compressive strength. Okay, because compressive strength and W by C ratio, they have an inverse relationship. Okay, so that's why we need to make sure that this extra water that aggregates are consuming, okay, for getting saturated, we add above this 160 kg that we added. Okay, so this is known as the water correction. And how much water correction is needed, it will depend upon the grade of aggregate also. Okay, some finer aggregates have more water demand, coarser aggregates have less water demand. Okay, now, if we consider each aggregate grain as spherical, okay, then specific surface area we can estimate as total surface area of aggregate pi r square upon total volume of aggregate, which is 4 by 3 pi r cube for a sphere. So it will be nothing but 6 upon diameter of aggregate. I guess there's some doubt. Okay, there was again a problem of disconnection. Again, there was some problem of disconnection on my side. I'm sorry for this issue, but there is some network instability today in our campus. Can anyone tell me from which slide the problem showed up? At which point? I'll try to change my
In
network
the
to.
fineness modulus,
What?
In the finance modulus,
So was fineness modulus discussed, or was it pending? Hello.
we are hearing.
Was fineness modulus discussed or completely, or was it fine pending?
Yeah, actually, while the end of the finance modulus slide it was cut, and I have raised one question that that finance modulus limits where it is mentioned. I mean, is there any code standard for that?
Okay, so we discussed
Like
about.
from less than 2.2.
Okay, so it was like almost covered. Okay, so I will just repeat fineness modulus. Okay, fineness modulus is nothing but a number. Okay, when we have the cumulative percentage passing data like we did in this question, what we do, we add this data. Okay, suppose for fine aggregate it is 16 plus 8 plus 4 plus 2 plus 1. So we add this number. Again, there is some network issue that is going on. Oh no, it is stable right now. Okay, so what we do, we add this number and we divide by 100. Okay, so this is what we discussed here, by adding the cumulative percentage retained on a standard sieve size and dividing the sum by 100. Okay, so the number that we get, it is known as the fineness modulus. So for concrete, it is desired that fineness modulus should be in between 2.2 to 3.2. Okay. Higher fineness modulus will reduce the water demand and lower fineness modulus will increase the paste demand. That is what we discussed. Okay. Now, after fineness modulus, the
It
second
is mentioned that finance modulus limits or where it is mentioned. I mean, is there any IS standard for this or
I
any
guess
other
it
standard?
is something mentioned in the IS code. I will also just confirm once and by next session or by the end of this session. Okay. I
Okay,
took
fine.
this
Okay.
from the professor's slide, so I just need to clarify this once, whether it is there in some code or not.
Okay, fine.
Okay, so after fineness modulus, second was surface modulus. Okay, so it is clear from the term itself, surface modulus represents the specific surface area of aggregate. Okay, so when we talk about aggregates, I will keep out of presentation mode so that I can see when network disruption happens. When I go to the presentation mode, I am not able to see that. Okay, so specific surface area, when I talk about, so this is the area. Okay, if this is my aggregate, what is the surface area of a aggregate? It is known as the specific surface area. Okay, and why this specific surface area is important? So this is the total surface area per unit kg of aggregate that is available to us. So if I have 1 kg of aggregate, what is the total surface area of aggregates that are available in that 1 kg? It is known as the specific surface area. Again, okay, there's some network issue. Okay, so what is the total surface area of aggregate available in per unit aggregate volume? It is known as the specific surface area. So you can see in this formula also here. Okay, it is the total surface area of aggregate divided by the total volume of aggregate. And why this quantity is important? Because it is used to estimate the water demand or workability of concrete. Okay, so if I have fine aggregate, what will happen? I will have higher surface modulus. Like we talked for cement, finer cement has more surface area, which is more which has more which is more reactive. So similarly, if there is finer aggregate particle, it has higher surface area, so it has more water demand. Okay, and if there is coarser aggregate, it has smaller surface area, then it has lower water demand. Now, what is water demand here? So, the aggregates that we are taking, whether it is dry aggregate or moist aggregate, it also is very important. Okay, if we are taking a very dry aggregate, what will happen? It will absorb water from concrete. Okay, so that water that aggregate absorbs initially to become saturated, it is known as water demand. And this term is very important in mixture design. Why? Suppose you make a concrete with a W by C ratio of zero point 0.4. Uh, just give me a second. You make a concrete with W by C ratio of zero point 0.4. Okay, so suppose for 1 meter cube of concrete you were adding 160 kg water. Now what happened? Your aggregates are dry. Okay, so when as soon as you will add water in concrete, aggregates will also absorb some water, because aggregates are porous in nature. They also have pores inside them, na? So they can absorb water. Higher water present concentration is outside, lower water concentration is inside, so water will migrate into the aggregate pores to saturate the aggregate. Okay, suppose 10 kg water is absorbed by the aggregates that you have added. So what will happen? The W by C ratio that you have in concrete, it will reduce maybe till 0.38 or 0.37. Now what is what this will cause? Okay, so we know that W by C ratio, it is important for strength of concrete. Okay, as W by C ratio decreases, the strength of concrete increases. So whatever we were designing, we may not achieve that strength or that durability of concrete. Why? Because aggregate has absorbed water from concrete which was there for cement hydration. Okay, so that's why whenever we do mixture design, we add moisture correction or water demand of aggregate. Okay, and this water demand, how we know about these water demand? Based on the aggregate gradation. Okay, so fine aggregates, they require have more water demand, while coarse aggregate, they have less water demand. Okay, so even in practice, if you take 1 kg of aggregate and you keep them in oven and you check how much moisture they have lost, you will find fine aggregates loses more moisture because they absorb more moisture from environment, because they have larger surface area which is available for environmental interaction. Okay, so this is the importance of surface modulus. Okay, so if we considered a sphere, okay, so my total surface area of aggregate will be nothing but 4 pi r square. Okay, and my volume of aggregate will be 4 by 3 pi r cube. Okay, so if I solve this equation, it will come out to be 6 by d. So d is the diameter of aggregate. Okay, so this is the specific surface area of a single aggregate. Okay, now for a aggregate having size between two sieves, so we know we classify aggregate based on sieve sizes. So it is between two sieves. Suppose it is between 2.36 mm and 4.75 mm. Okay, suppose in between these two sieves we have aggregate. Okay, so we can say specific surface area is nothing but 6 upon geometric mean of these sieve. Okay, so if you know how these sieve sizes were categorized. Okay, initially we talked about different sieve size: 150 mm, 300, 600, 1.18. So these are in geometric progression, they are in a multiples of each other. Okay, it is like 150 to 200 two times, then again two times, then almost two times more, then almost two times more, then almost two times more. So these are in geometric progression. Okay, so similarly, here specific surface area, if you want to determine based on sieve passing, so if it is 2.36 passing and 4.75 retaining, then specific surface area of that aggregate we can determine as 6 upon geometric mean size. Why we are determining like this? Because not always we'll get an aggregate which is spherical in nature. Okay, not always we'll have a perfectly sphere aggregate. So that's why for those aggregates we need to take a certain different measure of size, and that's why we are taking geometric mean of sieve size. Okay, so it is 6 upon di into di minus 1 square root. Okay, that is how we define geometric mean of a number, of two numbers. Okay, so since it is in geometric progression, we know di plus 1 is 2 times di, or it is 4 times di minus 1. So it is like 2.36, 4.75, 10. So they are in geometric progression. They have a factor of 2 between them. Okay. So if sieve 0, so if 0 size is my 75 micron and first size is my 150 micron, then specific surface area of aggregate between these two sieves of a single aggregate for one aggregate. Okay, for one aggregate piece, it will be nothing but 6 upon square root of 75 micron and 150 micron. Okay, so this was for one aggregate. If I know how much aggregates are there, then I can calculate the specific surface area of all aggregates between 75 and 150. Okay, so similarly, if I know all aggregates between different sieve sizes, I can calculate the total surface modulus. Okay, and since it is in geometric progression, so it will be 565.556.7 into percentage of aggregate between 75 and 150 micron plus percentage of aggregates between 150 micron and 300 micron divided by 2, because these are in geometric progression. So next term will be 565.7 divided by 2 and so on. Okay, so like that this equation is arranged. Okay, so I know there will be some confusion here, like what is geometric progression, why I'm doing divided by 2 here, why there is no factor for 150 and 300 also. So just do this calculation. Okay, do this calculation for all combinations. So this was for 75 to 150. Now do this calculation from 150 to 300. So you will get a number which will be around 332.35 or 332.3, which is nothing but 565.7 divided by 2. So that's why we took a 2 inside and we took 565.7 common. Okay, and so on. Okay, so this is how we determine the surface modulus. Okay, now to understand how we do this calculation, let's solve two numericals. Okay, so in this question I have given you gradation versus cumulative percentage retained. Okay, for each sieve size, and I want you to calculate the fineness modulus and comment its suitability for use in concrete. Okay, so this was the table that we saw for suitability of use in concrete. Just tell me what is the fineness modulus first of this fine aggregate batch. Okay, you have the data for sieve size versus cumulative percentage retained. In the meantime, if anyone has any doubt in the discussion till now, due to that disruption in network, you can ask. Just give this question a try. Was anyone able to do the calculation? Can anyone tell me what is the fineness modulus? So just remember here. What was it? Cumulative percentage retained on each sieve size divided by 100. Okay, so just do that calculation. So it will be 5 plus 15 plus 35 plus 60 plus 85 plus 95 divided by 100. So So this is coming out to be 2.95. Okay, so this is the fineness modulus of my fine aggregates that I have taken right now, and this is coming in this category. Okay, so it is in the category of coarse sand, which is still suitable for use. Okay, it is not bad. Okay, not very high, not very low. Okay, so this is how we do the calculation of fineness modulus. Next is question. Next question: a mixed aggregate is given to us. This is fine aggregate sample only, not mixed. Okay, and we know the cumulative percentage retained, the same data as it was here. We need to calculate the surface modulus of this aggregate. Okay, so in the last question you calculated fineness modulus. Now here I am asking you to calculate surface modulus. So can anyone tell me how surface modulus you will calculate? Just remember this equation. Okay, so P was here percentage passing. Okay, that we need to get. Any idea how to do the calculation here? Okay, I will just tell you. Okay, so right now we know the cumulative percentage retained, but this won't give us the data of what is the size of aggregate between two sieves. So what we'll do, we'll first calculate cumulative percentage passing, which is nothing but 100 minus cumulative percentage retained. So 100 minus 5 is 95. 95 minus 100 minus 15 is 85. Then 65, 100 minus 35, 100 minus 60 is 40, 100 minus 85 is 15, then 5, and this is 0. Now we need to get percentage passing between two sieves. Okay, so what is percentage passing through 4.75 mm and retaining on 2.66 mm? So it will be nothing but 95 minus 85. So 95% aggregate are passing through 4.75 mm, and out of that 95, 85% aggregates are passing through 2.36 mm also. So how many aggregates are retaining between 4.75 and 2.36? It is 95 minus 85. So it will be 10%. Okay. Similarly, 85 minus 65 will be 20%. 65 minus 40 will be 25%. 40 minus 15 will be 25%. 15 minus 5 will be 10%, and 5 minus 0 will be 5%. So this data that we get here, just understand, 10% aggregates are passing through 4.75 mm sieve and retaining on 2.36 mm sieve. Okay. Similarly, 20% aggregates are passing through 2.36 mm sieve and retaining on 1.18 mm sieve. So this is what this data means. Okay. How you can understand this? Just go back from percentage passing to cumulative percentage passing. So you will get the idea how this number is corresponding to what we are saying. Now we need to give the designation, what is P0, what is P1. So P0 we gave the designation to the smallest sieve. So for this sieve was P0, then this is P1, this is P2, this is P3, this is P4, and this is P5. So P0, this was the value that we calculated here. Okay, for sieve passing through 0.75 mm and retaining on 0.150 mm. Okay, so this, so there will be one more sieve here in between. Okay, so it is, yeah, there will 75 micron and then 150 micron, 0.075 and 0.150. Okay, so this is P0 and this is P1, P2, P3, P4, and P5. Okay, so we know percentage passing through each sieve designation, so we can put, simply put that in this formula. Okay, so what we'll get, 565.7 times P0 is 5, P1 is 10 divided by 2, then it is 25 divided by 4 plus 25 divided by 8 plus 20 divided by 16 plus 10 divided by 32. Why this number like 2, 4, 8, 16, and 32? Because sieves are in geometric progression. Okay, so when you will do this calculation, it will come out to be 565.7 times 20.9375, which will be equal to 11844 specific surface area will be this per meter cube of per centimeter. Okay, because it is area upon volume, so it will be 11844 centimeter inverse. Okay, so this is how we do the calculation, and all for all these things sieve analysis is important. Okay, I hope both questions are clear to everyone. Any doubt in these questions?
No, sir.
Okay, so let's move ahead. So after size classification, we have shape of aggregate. Now, why shape of aggregate is important? Because it helps us to the shape of aggregate can affect the workability, strength, and durability of concrete. Okay, so how different shapes of aggregates can influence the bonding with cement paste, the void content in concrete, and the W by C ratio, which can impact the overall concrete performance. Okay, so based on the shape, there are six classification: round aggregates, irregular aggregates, angular aggregates, flaky, elongated, and flaky and elongated. Okay, so what are rounded aggregates? Which have smooth surface. They are completely spherical in nature. Okay, they are naturally occurring smooth surface aggregates like river gravel. Okay, so they have high workability but poor strength because there is poor interlocking between aggregates. Then there's irregular aggregates, which are weathered aggregate, which have uneven surface like this. Okay, so they are opposite to round aggregates. They have lower workability, but since they are irregular in shape, they can make, like, there can be good interlocking between aggregates, which can improve the strength of concrete. Then there's angular aggregates, okay, which have sharp edges like this triangular shapes and those. So they have lower workability due to rough texture, and they have higher friction between each other, which can give higher strength due to proper aggregate interlocking. There's flaky aggregates, which are thin and elongated. Okay, which are thin and elongated compared to width. Okay, there's elongated aggregates which are have very high dimension in one section and very low dimension in another two dimensions. Okay, so these flaky elongated aggregate, again, they have poor workability and poor strength also. Why? Because of their surface nature. They are plate like surface through which crack can propagate, so they are poor in both workability and strength. And there are some aggregates which are both flaky and elongated. Okay, so what type of aggregates generally we need? We need irregular aggregates. Okay, because they can give better strength. Okay. However, if we our importance is on workability, then we need rounded aggregates. Okay, so there are different, suppose we have a irregular aggregate, so how we classify whether it is flaky or elongated or what. Okay, so there are different tests that are defined in Indian standard. Okay, so there is flakiness index text, we determine the percentage of flaky particles. So later on when we talk about properties of aggregate, we'll talk about this more. We'll see a scale where there will be different size openings through which we can pass the aggregate and we can get the mean flakiness index of aggregate. Okay, then similarly there is elongation index of aggregate, okay, which can help us to determine the percentage of elongated particle. Okay, and there is angularity factor, okay, which can determine us what how much angular my aggregates are. Okay, so these three factors, they help us to determine the shape of aggregate. Then finally, there is aggregate classification based on surface texture. So apart from shape and size, the texture of surface is also important, whether it is rough or smooth. Okay, rough aggregates and smooth aggregates, why they are different? Why they are different from each other? Because they can define the bonding nature of aggregate will with cement paste. Okay, a rough textured aggregate is preferred for high strength concrete because they have good bonding nature. However, smooth aggregates is preferred for workability because it can easily let cement paste flow over its surface, which will improve the workability. Okay, so surface texture again is of different types. There is glassy aggregate, which are very smooth. Then there are smooth aggregate, which are like polished, not very smooth but not rough. There is granular aggregates which contain small grains on the surface. There is rough aggregates which are irregular and pits on the surface. There is crystalline aggregate, okay, and there is honeycombed or porous aggregate, okay, which have lot of pores, so they have lot of water demand in them. Okay, so this is how based on the surface texture also we can classify aggregate. Okay, so just try to answer these three simple questions which are based on shape and the texture of aggregate. And in the meantime, if you have any doubt regarding shape and the texture of aggregates and how it is influencing the properties of a concrete, you can ask. Okay, if there are no doubt, just try to just tell me the answer one by one. Okay, question number 5 is which type of aggregate shape provides the best interlocking and bonding with concrete?
Angular.
Why is that so? Can you tell me the reason also?
Higher velocity.
Okay, so if you see angular aggregates, when we'll add in concrete, they will be like they will interlock with each other, and there will be less pore space which is will be left between them. So less amount of cement paste will be required to bond these aggregates together properly, and that's why concrete bond strength will be higher. However, if we have rounded aggregates, so suppose this is one aggregate, this is one aggregate, this is one aggregate, so there will be higher pore space between such aggregates. Okay, and if cement is not available to completely surround the aggregates, all the aggregates properly, then the strength of concrete will be compromised because of the presence of these pores, which will be a problem. So when we talk about interlocking in bond strength of concrete, angular aggregates are preferred. Okay, which surface texture leads to higher water demand in concrete? Can anyone tell me the answer for question number 6? Yes, the correct answer is rough aggregates. So smooth aggregates, they have the least water demand. Glassy aggregates have the least water demand. Rounded aggregates, they will have lower surface area compared to a rough aggregate. Okay, rough aggregates generally they are irregular in shape, they have small holes, they have irregularities at the surface which can capture the water, which can increase the water demand. Okay, in concrete. Okay, so that's why these aggregates have higher water demand. Elongated aggregates affect concrete. Why elongated aggregates affect concrete? And why C? Someone wrote C as the answer. Can anyone tell me why it weakens the concrete structure? Okay, the correct answer is C only. Just try to understand what is happening. Suppose this is concrete and this is one of my elongated aggregate inside concrete. And due to load action, there is cracking in concrete. So what happens generally as we'll move ahead, we'll talk about ITZ, interfacial transition zone, which is the surface between the surface of aggregate and cement paste, the interface between cement paste and aggregate. So this ITZ, generally when we talk about cracking of concrete, we say that crack goes through ITZ. Okay, and once multiple cracks they connect, okay, they eventually cause failure of concrete. So when we have elongated aggregate, we have a bigger ITZ area that is available, which will provide easier access to this crack to grow over the surface of aggregates. And that's why they decrease the strength of aggregates, because they ease the growth of crack through their surface. Okay, crack will easily grow along the surface of elongated aggregates as it is smooth and it is giving a clear path for crack propagation to happen. Okay, so once when we'll talk about aggregate ITZ, the strength of concrete, how ITZ affects the strength of concrete, it will be clearer to you about elongated aggregates. Okay, let's move ahead now and talk about one of very important property of aggregate, which is known as packing density. So if you recall the first slide that we'll discussed today about aggregate, I will just go to that slide. We said why aggregate are used in concrete, and we mentioned one important point: they reduce the overall cost of concrete by acting as a filler, minimizing the amount of cement required. Okay, now if aggregates are acting as a filler, better will be the packing between aggregates, the lower will be the cement demand in the aggregates, the cement demand in the concrete. Okay, so that is why packing density comes into picture. So by packing density, we simply mean the volume of solid to the bulk volume of uh, the uh, bulk volume of solid particles. Okay, so higher is the packing between aggregates, will say that lower will be the cement required to densify concrete. Okay, and what is packing density? The volume of solid upon bulk volume of solid particle. Now what this bulk volume includes, it includes the volume of the solid portion and the volume of the pores between solid portion. Okay, so that is why we have Vs upon Vb. Vb is my aggregate volume, and VB, bulk, is my aggregate volume plus the void volume, the air voids which are trapped between aggregates. Okay, so if I have higher packing density, it means that my air voids are very low. Okay, and if I have higher packing density, my aggregate will be acting better as a filler, and they will further minimize the cement demand in concrete. Okay, that's why packing density of aggregate is talked about. Okay, so if we simply write this in mathematical terms, we have seen PD is nothing but Vs upon Vb. Okay, so if we try to relate packing density with porosity, so how it will be related? Okay, I will just delete this. So it is nothing but Vs upon Vb. Okay, so we can write this equation as Vs upon what is bulk volume? We know it is solid volume of aggregates plus volume of air voids which are trapped between aggregates. So that's why I've written it as Vs upon Vs plus Va. Okay, so in this numerator, I will add volume of air voids and I will subtract volume of air voids. Okay, so I am adding and subtracting Va. Okay, so if I add and subtract Va at the numerator and keep denominator as the same, and I separate this part. Okay, this is one of my part. Okay, I will just use a pointer here. So I will separate this and I will write this separately. Okay, so Vs plus Va upon Vs plus Va will be equal to 1, and this will be equal to Va upon Vs plus Va. Okay, so what is this? Volume of air voids upon bulk volume, and this is nothing but porosity in my dry aggregate pack. Okay, so suppose this is my container, and in this container I filled aggregates. So what is the percentage air void in this container? It is known as the porosity. Okay, so packing density is nothing but 1 minus porosity. So lower is the percentage of air voids between aggregates, higher is my packing density. Okay, so what is the benefits of having higher packing density? It increases the workability or strength of concrete, and it improves the dimensional stability of concrete. Okay, why? How? Because now less amount of paste is required for aggregates. Okay, and more paste, if less amount of paste is required for aggregates, the remaining paste it will contribute to workability of my concrete. Okay, and the cement content demand will also decrease since aggregates are filling the concrete properly, they are compacting the concrete properly, so less cement is required. So my thermal compaction issue, shrinkage issue, expansion issues all will be resolved since I am using less cement. Okay. I hope this initial slide of packing density was clear to everyone, because the whatever we are discussing ahead, it will be based on packing density only. Okay. The next 5-10 slides. So for that, it is important that you understand packing density properly. Any doubt in packing density term right now? Just forget about cement, paste, or concrete here. Just think about dry aggregates filled in a container, and how much voids are there between aggregates. That is my porosity. And packing density is total volume of aggregate in that container upon total volume of container. Okay, so
How do you find out the porosity?
porosity is nothing but we know the total volume of container, suppose it is 1 liter, and we know the total volume of aggregates that we have added, so remaining volume is the porosity.
Okay, thank you.
Okay, that's why we derived this equation here. Va upon
Okay.
Vs plus Va. So Vs plus Va is the total volume of my container. So in this container, the entire volume is occupied either by aggregate or by air void. Okay. So the percentage of volume occupied by the air voids, that is the porosity of the system.
Can you give some example calculations?
What do you mean by example? Suppose I have 1 liter bucket. Okay. And in this bucket, I try to fill aggregates. Okay. of say, I try to fill circular aggregates of say 5 dia. Okay, so what will happen? First I will fill aggregates. Okay, it will go till this bottom portion, aggregates will arrange themselves. Then there will be one more layer at the top of the bottom layer. Slowly aggregates will come till the top. Okay, now I have filled the entire bucket with the aggregates. Okay, and I know volume of each aggregate. Okay, and I know how much quantity of these spheres I have poured in this bucket. So I can calculate the total volume of aggregate inside the bucket, and I know the total volume of bucket also. Okay, so the remaining 1 liter minus volume of aggregates is my volume, which is occupied by the pores which are present between the aggregates. Okay, and that volume of pores that are present in this 1 liter bucket, it is the porosity of the system. Is it clear now?
Can you repeat once, please? I couldn't understand.
See, why I guess your doubt is why there is porosity here. Okay, because of the aggregate shape. Okay, this is my container. This is my first aggregate. This is my second aggregate. This is my third aggregate. This is my fourth aggregate. Then again at the top, one aggregate, two aggregate, three aggregate, fourth aggregate. Then again, one, two, three, 4. Okay, so total bucket volume was 1 liter. I have filled 12 aggregates. Okay, suppose each aggregate had a volume of say some volume V, you assume VA. Okay, so total volume of aggregate inside the bucket, it is 12 times VA. Okay. Now I can't fill aggregate further. I have only single sized aggregate that are in the system. Okay. So what is the volume of pores inside this bucket? How much voids are there? Air voids are there inside the bucket. What is the volume? It will be nothing but 1 liter minus 12 times VA. And this is my porosity. Okay. Volume of
Yeah,
pore upon total volume of container.
seeing angular aggregate in concrete, how I can identify the porosity for angular aggregate? For how I can identify volume of angular aggregate because the size is different. If it is
Ah,
20 mm below aggregate, yeah, in this case, how I can find out?
So for
Is there
that
any
there
other
is,
method?
yeah, I got your point. Like for angular aggregate, how we'll get the volume of that aggregate. For circular aggregate, it is easy to identify, but how for angular aggregate? Okay, so generally there is one test that is known. Well, like here we talked about angularity factor, na. So in angularity factor, there is one term of volume of aggregate also that is there. Okay, so how we can determine volume of aggregate? Simply by one method which is known as let me see what is that method. Okay, water displacement method. Okay, by Archimedes principle. Okay, so what we do in that method? Okay, we take a cylinder. Okay, and we pour the cylinder with known volume of water. Okay, so we know there is marking here in the cylinder. Okay, different depth, what different depth they represent in terms of volume. So suppose in this cylinder I have poured water up till 500 ml. Okay, now I add my angular aggregates in this bucket. Okay, so after addition of angular aggregates, what will happen? The volume of container, it will increase. It may go from 500 ml to 700 ml. Okay, so what is the volume of aggregate in this system? It is 700 minus 500 because this is the increase in volume that happened due to aggregate addition. Okay, so this is how we can calculate volume of single aggregate. Okay, so when I added one aggregate, what was the increase in the volume of the container? Okay, that will define the volume of that aggregate. Okay, so this is one of the method. This is known as water displacement method.
Yeah, okay, fine, but every aggregate have different sizes.
So here
So
right now we are talking about single aggregate, not of different size. This is just single aggregate.
yeah, that's fine. I am asking practically we are using angular aggregate, which is used in the concrete. So to find out the packing density for angular aggregate,
Hmm.
on the whole, how I can find out, then only I can design my, I can perfectly design my concrete, right?
So right now, this theory which was built for packing density is it was started for a round aggregate system only. Because when we talk about angular aggregates, it is not very easy to calculate volume of each aggregate. Okay, not each aggregate will have same shape, same size. Okay, so while understanding packing density, just think of spherical aggregates. Okay, the same concept will work for angular aggregates also, but it will be a little complicated because calculating the volume of angular aggregate is not that easy. Okay, for each aggregate we need to calculate the volume. Here it is well defined shape, so for each aggregate it is easy to know the volume. Okay, now this concept that you will be understanding in next few slides, just try to understand how a multi-sized aggregate system changes the packing density and how it is different in a single-sized aggregate system. That is the point here right now to understand.
Yes. Okay.
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 So, so like we discussed in this problem, what size of aggregate we are taking, it can significantly influence the packing density. Okay, so if we are taking mixture of a single sized aggregate and cement paste, then to fill the gaps between the aggregate particles and to drive away the air voids inside concrete will require higher volume of cement paste. Okay, so in this diagram if you see, we require cement paste to completely fill this gaps. Okay, and to coat the aggregates also and to have a single layer coating between aggregates also, so that aggregates are bonded. Okay, so volume of cement paste that we require, it is more than the volume of gaps which are present between the aggregate skeleton. Okay, now suppose it is not single sized aggregate, we have multi sized aggregate system. So what will happen, the smaller aggregates, they will go inside the pores of bigger aggregates and they will reduce the voids that are present in the aggregate system. So the amount of cement that we require to fill the gaps between aggregate, it will also reduce. Okay, so lower cement will be required to efficiently pack the concrete. Okay, so what is the benefit of using multi-sized aggregate, the volume of cement needed to fill the gaps between the aggregate will be reduced. And suppose we are not reducing the volume of cement, suppose I required 10-meter cube cement initially in single sized aggregate system, while in multi sized aggregate system I required 7-meter cube of cement paste. Okay, now I know it will work with 7-meter cube also, but I am keeping 10-meter cube only. So what will happen, the remaining cement, it will disperse the aggregate. Okay, it will form coating between aggregates and it will provide the workability to concrete, it will allow concrete to easily flow. Okay, if my concrete is packed very strongly, then it won't be able to flow, it will be very stiff. Okay, so to increase the flowability, we'll have extra paste that will disperse the aggregate from each other and it will fill the gaps between the aggregates, because there is excess of paste that is present in the system. And when it will disperse the aggregate from each other and make a fluid layer between aggregates, it will increase the workability of the concrete. Okay, so either we can work with the lower quantity of cement, okay, that is sufficient to fill the air voids, or we can have higher quantity of cement and improve the workability of concrete. Okay, so same concept you can understand from this image here also. Okay, so you can see figure 1, it is concrete which is composed of single aggregate only. So this is my aggregate. Okay, and the air voids between aggregates is the minimum cement paste that is required to completely fill the concrete. Okay, now if instead of single size aggregate, Again, there was some network.
Uh, yeah, yes.
From which slide it happened? Actually, when I'm going to slideshow mode, the network issue is happening. When I'm keeping at this mode only, the network issue is not there. So where was
I
I when I
think
was
it's
discussing?
the previous one, I think.
Which this slide?
Yeah, this one.
So this was complete, right?
Before complete of the slide.
Can you repeat what you're saying?
Yeah, you didn't cover all those things in this slide. Before that, your connection has disturbed.
At which point it got disconnected? What was the last thing that I said? Okay, I will just repeat. So when we take single sized aggregate, volume of cement paste is whatever we require to fill the spaces between the aggregates and a little bit to coat the aggregate. Okay. So, but if I am taking multi-sized aggregate, what will happen? Aggregate themselves will fill the voids between bigger aggregates. So the cement that is required for us to fill the air voids it will reduce. So it will have two implications. Volume of cement paste needed to fill the air voids will be reduced, or if we keep the same volume of cement paste, the excess volume it will disperse the aggregate and it will improve the workability of concrete. Okay, so the same thing you can understand from this figure here also. So figure A has different aggregates, single sized aggregate, and between aggregates the volume is filled by paste. Okay, now if I add smaller size aggregates here, if there is multi-sized aggregate system, so what will happen? Smaller aggregates will go between the pores of bigger aggregates. So they will reduce the cement required to fill the air voids. Okay. Or if I don't reduce the cement, so what will happen? Cement will coat the aggregate and it will disperse the aggregate from one another and it will increase the flowability of concrete. Okay, so with the same paste, we're increasing the flowability of concrete, or either we can decrease the paste volume and fill the entire voids which are present in the system. Okay, so this is why multi-sized aggregate systems is needed, so that we can reduce the cement demand, or with the same cement demand we can increase the workability, the flowability of concrete. Okay, so this entire image it was taken from this a reference that I have mentioned here. So this is a very nice small like 10-12 page article which is on packing density and high performance concrete. So if anyone wants to go deep into this concept of packing density, you can just refer to this literature. Just read this paper once. You will understand this image, how they came up with this idea. Okay, so here I will quickly move because this portion was already discussed in the lecture and we have already wasted much time in this repetition of discussion today. So for single sized aggregate system, we know from atomic theory there is simple cubic arrangement of aggregate, body centered and face centered. Okay, if I take circular aggregates. Okay, so if I take a small cell, a small cuboid inside concrete, so aggregates can be either present on the edges, or on the edges plus center, or on the edges plus body center of each face. So that's for this cube, I know the volume, I know how much aggregates are occupying this volume. So I can define the packing density of simple cubic is 0.52, for body centered cube is 0.68, and for face centered cube is 0.74. So whatever actual packing density we talk about single sized particle system, it will lie in this range only from 0.52 to 0.74. However, if we take multi-sized aggregate system, we can have a packing density of more than 0.74 also, more than zero point 0.8 also. Okay, how? So if you take two aggregates, B is coarser aggregate and A is finer aggregates. So total bulk volume is volume of pores plus volume of solid. So void ratio is volume of pores upon volume of solid. Okay. So this is how we can define a single aggregate system. We know the total bulk volume and we know the void ratio. Okay, so if I add B to A, okay, suppose I am adding coarse aggregate to fine aggregate. So what will be my total bulk volume? It will be nothing but bulk volume of A, which is already there, plus solid volume of B, which I have added to the system. And what will be my total solid volume? It will be solid volume of B plus solid volume of A. Okay. So depending upon what is the fraction of B you are adding to the system, you can determine the void ratio, how it is changing for a multi-sized aggregate system. Okay. So this detailed uh, for derivation of this equation you already saw in the course. So that part I will skip here because we have already have a lot of content remaining. Okay, so just understand the concept. When I will add coarser particle to a finer particle, based on the quantity of aggregates that I'm adding, the voids present in the entire system, it will reduce. And by how much it will reduce, it will depend upon how much aggregates I am adding to the system. Similarly, if I will add finer particles to coarser particles, so these finer particles, they will occupy the gaps between the coarser particle. So based upon the proportion of aggregates that I have added, again the volume void ratio of my system, it will decrease. Okay, based on the fraction of aggregates that I have added. Okay, so based on the interaction between these two curve, okay, when I add B to A or A to B, the based on the proportion of aggregate that I'm adding, we will see that we can optimize the packing of the entire system. Okay, so when I add smaller particle to a larger particle, initially it is small particles, there are few larger particles, there are more larger particle. So at one stage there will be a proportion of large particle and small particle which will give me maximum packing density or minimum air voids. Okay, so this is the concept of packing density of a binary aggregate system, how we can optimize the packing of the system. Okay, so just try this question once. Okay, based on the packing density concept, just give it a try. Okay, I know it, like I have not explained you the formula completely how it came, but if you have went through the course lecture, the same thing was discussed in the course lecture also. So just give it a try, whatever you understood from the lecture and how you place that into reality. Okay. So in question number 8, we have asked that binary aggregate system consists of coarse and fine aggregates. We know the void content of coarse aggregate alone. So there is coarse aggregate and I know how much voids are there in the coarse aggregate. I know there are fine aggregates and how much voids are there in fine aggregates. So in binary system. Now, if fine aggregates completely fills the void between coarse aggregate, then what is the packing density of the mixture? No, what is the packing? What is the proportion of fine aggregates required? Okay, if fine aggregates completely fill the voids between the coarse aggregate, what proportion of fine aggregate is required, okay, to achieve this state? So here you just need to use this equation. Okay, you know, when void content in coarse aggregate alone, it is 40%. Okay, so that is EA. Okay, void content in binary system where there is just coarse aggregate. So this is given to us 40%. X is how much coarse aggregate you added in fine aggregate, or how much fine aggregate you added in coarse aggregate. So that factor is determined as X. And EB is void percent in fine aggregate. So that is 30%. Okay. So when you will solve this equation, when fine aggregates completely fills the void between coarse aggregate, then we say that whether we add A to B or we add B to A, I will achieve the same void percentage. So it will be optimized when both this line are interacting. Okay, the void ratio of addition of B to A or A to B, when they will interact, it will represent the system which has minimum void ratio and maximum packing. Okay, so when we'll solve this equation, we'll get a percentage X, and that X percent is the proportion of a fine aggregate that is required to fill the voids between the coarse aggregate. Okay, so this is how we think about the concept. Can anyone give it a try for question number 9 and 10 also? So in question number 10, I have told there are 70% coarse aggregate, okay, which has packing density of 0.68, and there is 30% fine aggregate, which has packing density of 0.55, and this is a binary mixture. Okay, if fine aggregate fills 80% of the voids of coarse aggregate, what is the estimated packing density of the mixture? So this is a little difficult question to think right now, but still give it a try. I will wait for a minute. I will see if anyone can get the answer. And in the meantime, think about this question number 10 also, which is a MCQ type. Okay. So I guess you should not expect these kind of questions in assignment or in exam, but because it will require you to remember the equation or a little bit theory, but such questions which is based on if I add A to B, B to A, what is happening, whether it will densify or not densify, that things can come up in exam. But this question, it won't require any formula, it is just requiring a little logic in the thinking. So just give it a try once. I'll just write some hints to think. So if we know the packing density of coarse aggregate, how we determine the voids in coarse aggregate? It is nothing but 1 minus packing density. So 1 minus 0.68. So that is 32%. So this is my voids in coarse aggregate. Now what question is saying? If 80% of the voids in coarse aggregate is filled by fine aggregate. So 80% of this 32% is filled by fine aggregate. So that is 26.5%. Okay. So out of 32%, 26.5% I have filled by fine aggregates. So what is the estimated packing density of my system? So it will be nothing but the packing density that was there originally plus packing density that has been filled by the fine aggregate. So that is 68%. Originally it was there, and 25.6% is now filled by fine aggregate. So it will be 93.6%. So this is the packing density of the system. Okay. So sometimes question may sound confusing, but when you write the question in numerical terms of what it is saying, it can be simpler. Okay. So we know voids which are there in coarse aggregate, 80% of those voids are filled by fine aggregates. So we know how much is the packing density now. It is 68% plus the voids that are filled by fine aggregate in coarse aggregate. Okay. Anyone can tell me the answer for question number 10? If we consider a binary aggregate system which has cores to fine ratio optimized to get maximum packing density, if I have maximum packing density and still I apply compaction force, what will happen? Can anyone guess the answer? Okay, we have already optimized the packing density, and above optimization, I am still applying some force, some rod. Using a rod, I am compacting the highly packed system. Okay, so will it cause change in the packing density? Yes or no? Can anyone tell me? Okay, the answer will be yes. Okay, so when I apply some compaction force on an already packed system, what will happen? Due to the force that I am applying, aggregates will still try to rearrange. And when they will try to rearrange, it will further densify the aggregate. Okay, so if I have circular aggregates, okay, like this, okay, on application of force, they will try to slip across each other, and when they will slip across each other they will further densify in the process, and which will further reduce the porosity in the system. Okay, so even after achieving maximum packing density theoretically, the amount of compaction force that we are applying, it can further densify the system, okay, due to a rearrangement of aggregates. Okay, correct answer is B. Now we'll quickly move to the last part of the course of this session. Okay, I won't keep on screen slide because it will disconnect the network. So last is the properties of aggregate, and this is the simplest part in the entire course. Okay, because when we talk about properties of aggregate, most of the properties we have already talked. Okay, so there are three descriptions of properties of aggregate. There is physical property, there is mechanical property, and there is chemical properties. Okay, so in physical properties we have sieve analysis, fineness modulus, specific gravity, water absorption, and shape testing. In mechanical properties, we have crushing value, impact value, abrasion value, flakiness index, and elongation index. And in chemical property, we have alkali, aggregate reactivity, and soundness. Okay, so if we first talk about physical properties of aggregates, sieve analysis and fineness modulus, we have already discussed. Okay, earlier. Specific gravity, as we saw for cement, the same thing is done here. So we have a pycnometer and we record. In this pycnometer, there is a glass jar and there is a conical top with a small hole at the top. And we record four weights. W1 is the empty weight. W2 is weight of pycnometer plus aggregates. W3 is weight of pycnometer plus aggregate plus water. And then W4 is weight of pycnometer plus water. Okay. And we determine the specific gravity using this formula. Okay. Where this numerator W2 minus W1, it is the weight of aggregate in air, and this denominator W2 minus W1 minus W3 minus W4 denotes the weight of aggregates in water. So the ratio of this gives me the specific gravity of aggregate. Now, water absorption also we have talked. Okay, if I have higher surface area of aggregate, it has higher water demand. And how we can estimate the water demand? I will take one aggregate which is completely saturated with water and I will oven dry it. Okay, and I will record the difference in weight. So the difference in weight is due to evaporation of water. Okay, So evaporation of water upon weight of dried aggregate, the ratio will give me the water absorption of aggregate. And this is very important from design point of view. Okay. So a zero point 0.4 W by C ratio, it may become 0.36 if we don't take water absorption correction during design, which can hamper my strength and durability performance. Okay, so when later on when we'll talk about mixture design of concrete, we'll see at the end of mixture design we do the water correction. We add some water for aggregate absorption, we add some water for fine aggregate and coarse aggregate absorption. That correction we do. Okay. Then shape testing, also we have talked earlier, there is flakiness index and elongation index. So this testing is done as per IS 2836 guideline. So you can see this scale for flakiness index. Okay, so we pass each aggregate through this scale, and we determine the flakiness of the aggregate. Okay, and we see that the percentage of aggregate whose least dimension is less than zero point 0.6 times the mean dimension, it defines the flakiness index of aggregate. And elongation index we define using, this is for elongation and this is for flakiness index. Okay, so from these two scales we determine how much percentage of aggregates are passing, okay, through different zones. And how, and then using this index, zero point 0.6 times the mean size and 1.8 times the mean dimension, we determine the elongation index and flakiness index. Okay, so that is how we do the testing using these two scales to get check the elongation and flakiness of the aggregates. Then in mechanical properties, what do you mean by mechanical properties? Properties which are related to the strength of aggregate. So that's why this crushing value. Again, IS 2386 code. So here what we are doing, we filled aggregates which are passing through 12.5 mm sieve and retaining on 10 mm sieve in this mold. Okay, and we are applying load on this aggregate system. Okay, so we apply 400 kilonewton load for 10 minutes. Due to application of load, aggregates will get crushed. Okay, so we'll do the sieve analysis and we determine how much aggregates got crushed or how much aggregates are passing to 2.36 mm sieve. Okay, and if there is aggregate which are passing through 2.36 mmc, which if there are between 25 to 30%, that means the aggregates are of good quality. If a lot of aggregate crushing happens, this percentage passing will be more than 30%, then we can say that aggregates are weak or they are of no, they are not of good quality. Okay, so this is crushing test. We are filling the aggregates of a particular size between 10 to 12.5. We are applying crushing load on them and we are checking how much aggregates got crushed. Okay, similarly there is impact testing. So here what we do, at the bottom, okay, in this small container, we pour a very small portion of aggregate. Why pen is not working? Yeah, we pour a very small portion of aggregate here and we apply crushing impact load on the aggregate. Okay, so due to application of impact load, some of my aggregates will get crushed. So again I will do the sieve analysis and I will check how much crushing happened. That will give me the impact strength of the aggregate. Okay, and third one is the abrasion resistance of aggregate. So it is used to assess the hardness of aggregate. Okay, so how we produce abrasive action? Abrasive means rubbing of aggregates. What happens when aggregates rub across each other? So when two rough aggregates will slide across each other, they can cross wear and tear of their surface, they can degrade each other. Okay, so this degradation of aggregates, this is known as abrasion. Okay, and this is used to assess the hardness of aggregate. Okay, so how we determine this? For this we need to know the grading of aggregate first. Okay, once we know the grading of aggregate, there is chart that is defined in the IS code. Okay, so we pour, suppose 5 kg aggregate we have poured in this Los Angeles abrasion testing machine. There is this lid. Inside this lid, we pour the aggregate. Now, to produce abrasive action, we add steel balls, okay, which will hit the aggregate and it will try to crush the aggregate. Okay, so how much steel balls we need to add? This is given in this IS code. So there are different grading scales that the code has defined, and for each grading scale of aggregate, they have mentioned how many number of balls and what is the weight of charge that we need to add. Okay, so those many number of balls and charges will be added in inside this. Charges means these pairs only. Okay, the steel balls. Okay, then we'll rotate this machine at a speed of 30 to 33 revolutions per minute for specified number of rotation. Okay, based on grading we define the rotation number also. Okay, so it is like for A, B, C, D, code says you need to rotate for 500 revolution. For grade E, G, and F, code says you need to rotate for 1000 revolution. So once these revolutions are complete, due to this rubbing of steel balls hitting the aggregates, there will be loss in the area of aggregate. Okay, size of aggregate. So again, we'll determine what is that loss in the size of aggregate, and from that we get the aberration resistance of aggregate. So everything, all the testing, it is based on the sieve analysis. Okay, how aggregates are getting crushed due to impact, due to crushing, and due to collision with each other and with steel balls. Okay, so this is mechanical properties of aggregate. And finally, there is chemical properties of aggregates. So we have alkali aggregate reaction. Okay, we want aggregate as an inert material in our system. But suppose aggregate has some reactive part, so it can hamper the concrete performance. Okay, so that reactivity of aggregate, it is known as alkali aggregate reaction. Okay, so aggregates, the silica that is present in the aggregate, if it is reactive, then it can interact with the cement paste and form some expansive products which is not desirable for us. Okay, so this alkali aggregate reactivity, how it is happening, in which kind of aggregate it happens, we'll talk later when we'll talk about durability of concrete. But right now, just remember, there is aggregate alkali reactivity. We don't want aggregate to be reactive. Okay, we want aggregate only as an inert material in the system. And soundness. Okay, so soundness, as we talked earlier, when we talked about cement paste, soundness refers to what makes a cement unsound when it is expansive in nature. So same thing can occur for aggregates also. When it absorbs water, it should not expand. Okay, so if there is impurities present in the aggregates which can cause the problem of soundness in aggregates, that is also not desirable to us, like clay or shell or wood. Okay, they can make aggregate unsound, or gypsum or mica or sulfides, they can also make aggregate unsound. So these chemicals also are not desirable for us in terms of inert nature of aggregate. And all these things, they come in the chemical properties of aggregate. Okay, so just to end the session, can anyone answer these three simple questions based on the properties of aggregates, just so that I can check whether you were able to understand this section or not? What will be the answer for question number 11? Specific gravity of aggregate is crucial for mixture design. A high specific gravity generally indicates what? What if I have high specific gravity of aggregate? Can anyone tell me the answer? Okay, high specific gravity means high density of aggregate, and if aggregates have high density, they have high strength. Okay, so such high specific gravity aggregates, they are used generally when we talk about high performance concrete or high strength concrete. Okay, so when we talk about strength of concrete, it doesn't just come from the hydration of cement and water. Aggregates are also very important component in strength of concrete. Okay, if we take recycled aggregates which are porous in nature, they can't give us very high strength concrete. Okay, for a high strength concrete, aggregate should be of high strength, high quality. And when we talk about high specific gravity, it will give us the high strength concrete. Okay, the soundness test of aggregate, it is conducted using which chemicals? Okay, so when I talked earlier in the previous slide, I didn't told you the chemicals that are required for soundness test. So these chemicals are potassium sulfate and magnesium sulfate. So I, as I told, if there are certain impurities that are present inside aggregates, they will interact with water and they can cause some formation of some expansive product inside concrete, which is not desirable for us. So how to check whether such impurities are present or not? We use sodium sulfate and magnesium sulfate. So what these sulfates do, they interact with the impurities inside concrete, inside aggregate pores, and they form products which are expansive in nature. So if we see formation of such crystal products on the aggregates, we say that aggregate is unsound in nature. Okay, so that is, this test is rarely used because mostly the aggregates that we get from natural sources, they are not reactive, they are almost inert in nature. So rarely you will see soundness test being conducted for aggregate anywhere. Okay, aggregates with high surface roughness and angularity generally results in which kind of concrete? So if I have an aggregate with higher surface roughness and angularity, what can I expect from the concrete composed of such aggregate? No, answer will be C. Okay, when I talk about angularity, what will happen? It will, aggregates will interlock with each other, and high surface roughness means they will have very good bond with cement paste. Okay, so overall these two things will ensure that aggregate packing is high and their interaction with cement paste is also high, so they will have high bonding with cement paste. Okay, and they will give rise to high strength concrete. High, for high workability, we need circular aggregates. Okay, for lower strength, we need porous aggregate. For lower permeability, again this angularity things can work. Okay, for permeability, so it will also result in low permeability, we can say, because there is proper packing in concrete. Okay, so this is how we talk about aggregates, how size affects, shape affects, surface texture affects, what is packing density, what happens in a single sized aggregate system and in multi sized aggregate system, and what are the properties of aggregates, mainly the crushing, the impact, and the abrasion property. Okay, so this was all for today. Thank you. So if anyone has any doubt in the entire session that we have discussed today, you can ask your queries, or any doubt regarding assignment questions that were there till last for the first week and the second week, that also you can ask.